Hi all, welcome to Geeks for Geeks. My name is Nitin Kaplas. Let's talk about today's problem. Our problem is Euler circuit in an undirected graph. Let's talk about problem first. So a problem is Eulerian path is a path in a graph that visit every edge exactly once, right? Eulerian circuit is a Eulerian path, right? Where we have to start and end on the same vertex, okay? Here we are given the number of vertex V and the adjacency list ADJ, which denoting the graph, okay? We have to find that there exists the Euler circuit or not. If it's there, we have to return 1 or say as true. If it's not, we have to return 0 in this case, right? So here we are given the note like given graph is connected, right? Given graph is connected. So the first example is we are given the V equals to 4 and edges are given, right? 4 edges are given and 4 edges are connected to each other, right? So it's a connected graph. So in this case the output is 1, right? Before going into the discussion of this question, let's first understand what's the meaning of Euler path, okay? So if I tell you the definition of Euler path, so the simple definition is the path of edges that visit all the edges in the graph exactly once, right? We have to visit all the graph nodes only one time, right? So before going into the example, let's first understand these 2 points. Here in this graph, not all graph is Eulerian path, right? Please keep in mind this point. You will understand this point later. And the second is be careful from which node you start from Eulerian path, right? From which node you are calculating that is a Euler path or not. Okay. So let's first understand these 2 points. So here suppose this is a graph, right? This is the graph which we are given, okay? So it's a undirected graph. Let me write here undirected, okay? So in this case, if I start from this node, let's start from this node. So we have to traverse every node or say as every edge only once. Let's check it. So I am starting from this. First I am going to this path, okay? Let me change the color first. Okay, so from 0 to 1 I am going through this path, okay. So 1 to 2 I am going to this path. Now we have two options. Let's go from this path first, right? I am at 3 right now. Again from 3 I go to the 4. Again from 4 I go to the 2. It means that I am successfully visit all paths. I am successfully visit all path or say as all edges, right? Exactly once time, right? So it means that if I start from this edge, right, my output is true in this case, right? My output is true in this case, right? Let's see second example. Suppose same graph we have, but I am starting from this edge, right? From this vertex, sorry, from this vertex, okay? So in this case, I have two paths. From 2 I can go 2 or 3. Let me first go to 2, okay? So in this case, again I have two directions. I can go to 1 or 3. Let me go to 3 first. Here I am going to 3. Right now from 3 I go to 4, okay? But when I am 4, again I am reaching to that node or say as that vertex, okay? So here again I am going to 2. So it's a cyclic part, right? So here if you see 1 and 0, I am not able to like visit that edges, right? So in this case my output is false. Let me check first again like second path. Right now if I am here, right, instead of going to 2 first, let me go to 3. After that I go to 2. Again I have two paths. Let me go here first, again here. So this is the end of it, right? So if you clearly see in the second path, I am not able to visit this this edge, right? So both the paths, my output in this case is false, right? So the condition is simple. Let me write here. Property of this is, first is, we have to visit all edges. First is this, all edges, right? Second is simple, once. We have to visit all the edges once, right? Okay. So I hope you understand what the meaning of Euler path, right? Simple. It's very simple. Let's understand now our main concept, right? Which is Euler circuit, or say as Eulerian circuit. So what's the definition of it, right? An Eulerian path which start and end on the same node, and this is also known as Eulerian cycle, right? Let's understand first, right? So before understanding the definition, please note this 2 points also. So let's first understand the noting point of this. So here, first point is, note all graphs as Eulerian circuit, right? It means that all the graphs, like you are given the 3 to 4 graph, right? All are not following the property of this, right? The second is, if the graph has Eulerian circuit at any point, at any vertex, right? Then you can start your path from any node. It means that if my graph follows the property of Eulerian circuit at any node, it means that you can start from any node, right? All the nodes have followed the property of it. Let's see the example of these nodes point here. For example, I am starting from this point, right? I am starting from this point. Now, where I can go? Let me go from to this path, right? Right now I am here. Let's go to this, right? Again we are going to this vertex. After that, going to this vertex. Clearly see right now. It's a little bit complex to see. So here I am going to this case, right? After that I go to this path. Okay. And right now I go to this path, right? Again I go to this path. Okay. Now from this I can go to this. Okay. After that, from this I go to this path. If you clearly see, the first property in this cycle, right? I am visit all nodes. Visit all nodes, or say as all edges. Okay, all edges. It's not a node. It's the edges, right? Let me write here edges. All edges. Okay. So the second point is, we have to visit once. If you clearly see my direction, we are visiting only one time, right? Third, and the most important, where I am starting now, that should be your ending also, right? Here my start is this and my ending is also this, right? Ending is also this. So these are the three properties of Eulerian circuit. Okay, hope you understand till now. So the second note is, if you see the second node, you can dry run this part also. If the graph has Eulerian circuit, then you can start from any path, right? From any node. Okay, so in this case I am starting from this, right? If you are starting from this now, let's start from this. If you start from this, right, and you go to path, right, this node is also follow the property of this Eulerian circuit, right? These three properties are also followed by this. Not only this, all the nodes, like this node, this node, this node, this node, this node, right? All the nodes are following the property of it. If your single vertex follow the property, right, as simple as that, you can do the dry run and check it's true or not, right? Now, so right now, if you see it, like it's a medium level problem, right? but it's very simple problem if you understand till now, right? So here the trick is very much easy, but to crack it, it's a little bit complex. So if you see here, the trick to solve this question is within the 2-3 lines, right? All the vertices have even degree. That means it follows the property of Eulerian circuit, right? Let's check it's working fine or not. So if you at this node, right? If you start from this node, let's start from this node, right? You are going from this path, now this path, now this path. So the first property you follow, right? All edges you visited, right? Now exactly once, right? It's also true. The third is start equals to end. Yeah, it's also true, right? This is my start and this is my end, right? In this case, if you see, its output is true in this case, right? Now let me do again dry run of this. If I am starting from 2, right? So it's a small, so you can understand it better. So let me erase this first. Okay. Now if I am starting from this, let's start from this. I am going to 3, again I am going to 1, again I am going to 2, right? So this is my start, right? When I start, this is my start and this is my end also, right? So this also follow the property of it. So that's the second point which we have to keep in mind. So let me start from this node now. Let me start from this 3 node or 3 vertex, right? This is my start. Okay. So the first I am going to this, again this, again this. So I am reaching to the starting point, right? So this is my end also. So that is true. It means that is true, right? Now let's see this example. So in this case, let me start from this case. This is my start, right? I am going to 2, right? After that, there is no any path, right? So in this case, my answer is false, right? My answer is false. Now, the trick to solve, let's check it's working fine or not. Let's check this. Now, all the vertex have even degree. Let's check this. What's the degree of this? 2 now. Its degree is 2. Let me write here. Okay. Here, what's the degree is? My degree is 1, 2. Its degree is 2. In this case, what's the degree is? Again 2. So, all the nodes or says all the vertices have even degree, right? It means that it follows the property and output is true in this case, right? We can solve with the help of degree part, right? Let's check this case. What's the degree of this? 2, right? What's the degree of this? 1, right? Only 1. Here degree is 1. So in this case also, right? Sorry, in this case I have odd degrees, right? It means that we have to return false in this case, right? All the vertices have even degree, right? That's the main part of this question, right? Now let's check for this case. Now in this case, if I am checking the degree, right? And from this example, like the one question came into mind, it's a even or 2 degree, right? So let's check how it is even, not exactly 2, it's a even, right? Let's check this case. Now, what's the degree of this? Degree of this is 2, right? What's the degree of this? Again 2. What's the degree of this? 1, 2, 3, 4. It's 4, right? What's the degree of this? 2. What's the degree of this? 2. So, all the vertices have even degree, right? Even degree. So, in this case, my output is true, right? My output is true. So, let's check now how this is working. For the 4 part, the degree is 4. If I am starting from 4, how it's working? Let's see this. Let me start from this node or this vertex. So first is I am going to 3 to 4, right? Now 4 to 5. here I am going 4 to 5, right? Now 5 to 3, right? Again to this path, again to this path, again I am going to this path, right? So here I am achieving all the paths, right? All the edges, right? The second is only once, right? Now third, start is equal to end. Yes, start is equal to end. So in this case, the third property is also satisfied, right? So in this case, it means that my output is true in this case, right? If this is true, all are true, right? Hope you understand this. Now, just try run a little bit of cases, like if you start from this, right? If you start from this, you can easily, like, you can follow the property of this, these three, you are successfully follow these properties, okay? Now, so let's code this now. Now, how we can check the degree? So degree is simply, like, for example, let's see this example first to solve this question. So here my vertices is v equal to 4. So the first is edge is 0 to 1, right? Second is 0 to 2, let me write here 0 to 2. Now 1 to 3 and 2 to 3, 1 to 3 and 2 to 3, right? It's undirected, so we can make it like that, okay? So in this case, in the question part, the adjacency list will be given to me, okay? So what will be the adjacency list? We can find the degree just comparing with the adjacency list size. Now here 0 have 1 and 2, right? If I talk about 1 having in the adjacency list is 0 and 3, right? Let me write here 0 and 3, and 3 having 1 and 2, okay? 1, 2 having 0 and 3, right? So if you clearly see, its size is 2, it means that degree is 2, right? Here 2, here 2, here 2, all are even? Yes, all are even. So give me the output as true in this case, right? Okay, so hope you understand this. Please do the dry run for this case, okay? If you do the dry run of this case, so 0's degree is 2, that's okay. If I am calculating for the degree of 1, right? So it's a 1 degree. So here I am returning false, right? So simple, we have to write this case. So let me do the coding part. So simply I am just traversing the vertices size, okay? Inside this, I just have to check its size. If at adj dot I dot size, if it's odd, we simply have to return false in this case. But if all the things are passed, all the vertices are passed, right, without odd, so we have to return true in this case. So let's check and compile it. Yeah, the compilation is good. Let's submit. Yeah, as you see, all the test cases are passed, right? So let's discuss about the time complexity. If you clearly see, we are just traversing the loop, right, up to v, so it's big of v, right? Inside this, we are just checking the size of it, which is constant, right? So what's the time complexity of this is? Time complexity is big of v, right? And here the space is constant. Space we are using here constant, right? Hope you understand this intuition and solution. Thank you so much.